As I said, my name is Alan Cohn. I currently work at Carnegie Mellon University Software Engineering Institute. We're a federally funded research and development center. Our sponsor is the OUSD R&E, so Under Secretary of Defense Research and Engineering. So my current role here is I'm actually a technical lead for a safety verification team. We're currently analyzing, doing verification and validation on an update to a modern Air Force weapon system. But before I came here to come work at the Software Engineering Institute, I previously worked at a defense contractor developing NSA Type 1 certified crypto boxes. And while I was there, I was also a member of the company's coding standard working group that was always working to ensure that we were in line with the NSA's guidelines and stay up to date with the latest languages. So today we're going to just cover a couple things. We're going to start with, why even have this talk? We'll then go into what does safety even mean in the context of code. I have an example of unsafe code that I'll walk through briefly, and then we'll round it out with what can we do about it, what steps can we take, and where can we kind of go from here. So to start with, right, the problem. I am inherently a C and C++ developer, and C and C++ is and has been under attack for a while. Right, the White House put out a report in 2024 in the Biden White House that basically talked about how all the memory safety problems with C and C++ is really, really dangerous. And CISA and the FBI followed it up earlier this year with another report saying that even using C and C++ elevates the risk to national security. All of these reports, and these are just two examples of a couple of them, all kind of stem from the same underlying opinion that that C and C++ are memory unsafe languages, and that is inherently raising the overall risk for all systems that are being used within the DoD and also being used in the commercial industry as well. So before we kind of go any further, I want to take a quick minute and just talk about what are the different types of language safety that we have, right? So we could start with memory safety, right? Which is, of course, what those reports were just talking about, thinking about spatial and temporal memory safety issues. But the reality is that those reports really only kind of scratch the surface when it comes to safety issues. There's many other different types of safety issues that we have to consider when we're looking at a programming language. We have to look at things like type safety, which includes unions and castings, right? We have to look at things like thread safety, which are, race conditions, concurrency, making sure that we're not locking ourselves up. And then, of course, there's kind of the worst of them all, which is undefined behavior, right? Which is unpredictable execution. Anything is possible. These are all really important concepts to consider when you're looking at language safety, and kind of to the credit of the federal government and their reports that they're putting out, C and C++ definitely have all of these problems, right? They have memory safety problems, type safety problems, thread safety problems, and undefined behavior. But one of the key takeaways that I have when I read these reports is that, addressing only memory safety issues does not make the program safe, right? And one of the key takeaways that I'm hoping to get out of this talk today that you kind of come away with is that we collectively as a community, as individual programmers, software engineers, software developers can help make our program safer, and we can actually address the memory issues to help make the program safe. Because at the end of the day, memory safety, which is what all of these reports kind of focus on, is not the only issue that can make our programs unsafe. So one of the examples that I want to kind of go through is an example of code we have called zombie code. This is a really kind of simplistic example to try to illustrate why it's not just memory safety issues that we want to worry about. So I'm going to kind of help orient you real quick to the code we're looking at. There is a global static T function pointer, which is basically, just a function pointer pointing to a function that takes of type int, right? We're initializing that function pointer to null. There's a detonate function that we're calling that all it does is print out kaboom and return 0. There's a set detonate function that just sets the function pointer to detonate. And then we have our main. You'll notice in main, there is a precompiled poundif1 in there. It calls the set detonate function, and then it checks to see if function pointer detonate is null, print out null, and then it returns by actually calling the function itself. So what do we think is going to happen here when I actually go to execute this? Well, obviously when a main is run, it's poundif1 in, which means set detonate's going to call. Set detonate will set the function pointer to the detonate function. So when we call this, because pointer detonate is not null, it'll skip that and just call kaboom. It should just call kaboom, right? And look at that. That's exactly what it does. Now, makes sense, very straightforward. Now I'm going to make one change, one character change to this. I'm going to change the poundif1 to a poundif0 instead. And when I do that, what do we think is going to happen? Well, set detonate isn't going to get called anymore because now it's going to be compiled out, right? So func pointer detonate should be null because it was never set. It should print null. And then when it goes to return and call the function pointer, what do we expect to happen? Well, it's null, right? As the if statement will prove. So we expect it to most likely segfault out or do something or crash, or depending on the processor you're running on. So when we run it, what happens? Wow. What happened here? Very weird. It hit null, but for some reason it still printed kaboom. And it's a very, very, very weird error that happened. So why did this happen? Kind of what occurred? Well, obviously we had a null function pointer, but the reality is that a null function pointer in the C and C+ in the C language is considered undefined behavior. So again, when undefined behavior happens, you don't know what's going to happen. In fact, in this particular instance, it turns into a compiler dependent problem. So in this case, the compiler can either return a null and produce an error, which is what we expected to happen, or in this case, the compiler can actually go in and assume that the code intended to assign the func pointer detonate to that detonate function. So why did this happen? And how do we, it's compiler dependent behavior. I ran this using the Clang compiler with the -O2 optimization. At the end of the day, if I had used the GCC compiler, if I had changed the optimization level at all, it actually would have had the first behavior listed where it would have just returned a null and produced an error. But instead, it ended up the compiler with that level of optimization, for whatever reason, the compiler vendor decided they was going to try to be smart and assume what I wanted to call in the first place. In this case, it was a combination of unused code and null function pointers combined to cause an unexpected form of compiler-dependent undefined behavior, right? It wasn't just one issue. It wasn't just the undefined behavior, but leaving that poundif0 code in there and leaving the set detonate, which when you put the poundif0 in becomes unused code, those two things together combined to create a compiler-dependent undefined behavior, which is very unsafe. Which, if we go back right to the four types of safety that I introduced in the beginning, neither of these two things are memory safety issues, but are still type safety issues, right? One that is 100% user dependent, right, which is having unused code, and the other, which is having null function pointers, which is the undefined behavior in the compiler, right? There's something that we could have done as developers to make our language safer in the way that we developed, but at the same time, the language was inherently unsafe because of the undefined behavior, right? So that was just one quick, real quick example looking at some C code on how different issues that are not necessarily memory safety issues can still have unintended and unsafe consequences on the code that we write. So, if I take a step back and I make the claim that C and C++ are inherently unsafe languages, so why not use other languages, right? Why not go in a different direction? And, to be honest, a lot of people have looked into doing that, right? So what I did was I took some of the more mainstream languages like C# and Go and Java and Ada and Rust, and I tried to put them on a graph of programming language safety versus embeddability, looking at, how we can use C and C++ in an embedded, flight type software. And what I did was I went through and started thinking, are there languages that are better than C and C++? And I started to go through them, right? And, when you start with Go, C#, Java, you start looking at things that, those languages primarily use garbage collection, and that starts running into problems when you get to safety critical embedded systems where you need determinism. You're going to have temporal based garbage issues, right? You never know what's going to get removed where, the determinism kind of goes down the toilet. And from my perspective, when I look at, when my team is looking at verification and validation, we really put a high priority on our ability to reproduce results, and garbage collection kind of runs in the face of that. So what else can we do? Well, C and C++, as we already talked about, have memory safety issues, so those really aren't that great. Undefined behavior, we just kind of ran through an example of undefined behavior that can occur in a C language, right? Ada also has undefined behavior, though it's not as widespread as C and C++, so that's not great. And then, we get to Ada and Rust, which at the end of the day are going to have widespread adoption issues, right? Ada has already, by and large, been widely rejected, right? And Rust is certainly the new up-and-coming language. There are certainly more and more people who are, engaging with Rust and writing programs in Rust. But at the same time, it is a new programming language. It is still not being taught in schools and colleges, right? The workforce who is knowledgeable in Rust is small. And as we learned from other programming languages, think COBOL, right? Just having these widespread systems with millions and millions of lines of code that have already been deployed and have been around for decades and decades, we're going to have problems, replacing all of those with Rust. It's going to be a slow, time-consuming process. So at the end of the day, where does that leave us? And it kind of feels like, okay, C and C++ doesn't really have any clear heir apparent, right? We don't really have another programming language that's going to come in and say, C and C++ have all these problems, and this new language is going to solve all of them. While programming languages like Rust will, there's no guarantee that Rust will ever be widespread adopted and across the board in the relatively near future. So what can we do about that, right? Where can we go from here? And I think one of the most important things we need to think about is safety as a quality attribute, right? That there's really kind of two types of safety, right? There's the language safety, which is ensuring the correctness of code, mitigating programming errors. And then you have the functional safety, which is ensuring the design of the system protects both itself and its users. And of course, those two things come together to form system safety. But at the end of the day, and again, the key takeaway is we can make the language better. Language can only do so much. We can only rely on the built-in language features so much for ourselves. At the end of the day, safety relies on the programmer to ensure that we are using the languages correctly and safely and in the proper manner. So where does that kind of leave us? Again, kind of circling back, only you can make your program safe, right? The key takeaway here has to be, there are things that we have to do to ensure that we are utilizing programs safely. We have to prioritize safety in everything we do. I think someone mentioned it earlier, right? You can't just verify in safety, right? You can't wait until the end and try to add safety in on top. You have to prioritize safety from the very beginning. You have to build it into your systems from the ground up. You have to utilize and improve the standards and tools, which I'll get into some small examples on the next slide. You have to engage with the larger community. I went to CPPCon last year. I don't know how many of you went as well, but one thing that is very clear when I attend CPPCon on is the larger community is not really focusing on safety issues, right? They're focused mainly on performance. They're focused on making the language a little bit better, adding new features in, but safety is not really a primary focus. And that's why this community, the community here at the Flight Software Workshop, who care about mission critical, safety critical code, really need to start engaging with the larger, grander community and really try to show them that, hey, safety is a very important part of C and C++, and we need to make it better. And, you know, of course, one of the first things that we can do is start addressing the hundreds of known undefined behaviors that exist in those languages, just as a starting point. And of course, the last thing you could always do is consider the use of alternative languages. Like Rust. Again, not every application is going to be right for using a different programming language, but it should always be considered. No, with all the known problems of C and C++, if Rust will work, that's certainly something that you should do. So when we talk about those are kind of the larger concepts, but if we take a deep dive and think, okay, what can I do today? I'm a software engineer. I'm working on my project. I need to ensure that I'm doing things safely. What are some potential safety mitigations that we can put in place today? One is, we can put software mitigations in there. One example here is Miracle Pointer. I think Google Chrome, when they were going through and they were having all these pointer problems, they created this miracle pointer, and they tried to implement that to help resolve their issues, right? We could talk about hardware mitigations, looking at things like ARM memory tagging extensions, or the memory randomization. But we can do these things, and to be clear, right, we are already doing some of these, right? So if you look at like the ARM memory tagging extensions, you can look at things like stack canaries. If we're going to talk about built-in software mitigations, we are definitely doing things to make the languages better and safer. They are significantly safer than they have been previously, right? They are continuing to get better, but that doesn't mean that we still can't continue to improve what we're doing, right? We can do things like dynamic analysis using tools like Valgrind to look for memory leaks, use after free, things like that. Of course, you can do static analysis, but using static analysis is really not enough. And what I always like to tell my team and other government stakeholders that I work with is, at the end of the day, it is not just the static analysis, it's the adherence to coding standards, right? Not everything in a coding standard can be checked using an automated checker and a static analysis tool, which is why it's incredibly important that you not just do what is already captured in static analysis, but you also follow all of the other rules that are in there that might not be able to be checked in an automated fashion. And then, of course, and this is kind of the last thing, the last biggest takeaway, this is the thing that everybody can do today without needing any fancy tools or knowledge, and that's just be aware of what you're doing and utilize defensive programming, right? Think, how can I make sure that my language is safe and that I am doing things in the safest way possible as I go about writing my functions? Because at the end of the day, and again, key takeaway, kind of last point, right? We collectively, as software engineers, need to make sure that we are building our systems with safety in mind, utilizing the language safety features that we can. But at the end of the day, it comes back to us to make sure that our language is safe. And at that, I will take any questions that you guys have.
Let's give a round of applause, please. Yeah. Questions in the room, first of all?
So you talked briefly about coding standards. I just wanted to ask a sort of opposite question, as you probably feel usually. Is there a type of rule that you see frequently in coding standards that you think does not bring very much value and should go away?
I mean, I think just about every rule in coding standards is valuable. I think a lot of coding standards that I see still like to focus on things that are not necessarily as important as other things. I still see a lot of coding standards talk about, you know, the length of functions, right? The length of function names, the total length of files. Is there a particular one that I don't think is very useful? Not really. I think it really comes down to each person and each implementation and what exactly they're looking for and trying to evaluate. I know that at least in my experience, one that I've seen a lot of is you must validate every parameter prior to use in a function. While I think that's incredibly useful, a lot of times most functions just pass information through, right? They're not dereferencing it, they're not using it. And I think giving that example highlights my biggest issue, which is static analyzers themselves are incomplete in their ability to actually enforce coding rules. And a lot of times the implementation that the analyzer uses under the hood does not match what the actual implementation or the writing of that rule is. And I think that is probably the biggest gap.
All right, we'll take an online question regarding the adoption of Rust. Are you aware of efforts like Ferrocene? And they list several standards: SO 26262, IEC 61508, IEC 62304, qualified compilers for Rust.
I'm not familiar with those listed specifically. What I am aware that everyone is starting to look at Rust as a legitimate contender to replace C and C++ over time. The only point that I was trying to make that, where we stand today, when I look at the widespread use of C and C++ and all the memory safety problems and undefined behavior and type safety issues that I see across the board, it's Rust having a better language like Rust can't come soon enough, but unfortunately it still looks like it's kind of a far ways off at this point.
Okay, big one from in the room.
Hello, thank you for the talk. I really enjoyed. You mentioned the concept of defensive programming, which I have to admit is a little bit conflicting for me, because then if you do too much of this, you lose the expressive concept of the code. No, the code stops being readable, and then it becomes something that is maybe super safe, but extremely difficult to maintain and to follow. What is your opinion on that point?
Yeah, I've actually, in my experience, have actually seen it the opposite, where the more readable the code is, the more straightforward it is, the more easily understood it is, the safer it actually becomes. There's a lot of like when you start, I'll use an example. I'm sure a lot of you like using Lambda expressions. When I work in these mission critical, safety critical environments, we have very strict rules that say you cannot use Lambda expressions, because the expressiveness of that, a lot of stuff gets lost. What exactly is happening it's lost under the hood, and it becomes a lot harder for someone to ensure whether they're using things safely or not. Similar things like the auto pointer in C++, a lot of times we say don't use auto because we want that explicitness out there of what exactly is happening. So I think the more straightforward it is, the safer it is, but that's just my experience based on everything I've seen so far.
All right, let's thank our speaker again, please.